we're going to take our 60 plus or minus. When you multiply this out, you're going to get 4.186. When you add or subtract that to 60, you're going to get your confidence interval of 55.814, comma 64.186. Moving along, I don't know why that moved down. Just going to erase it. And I'll rewrite it real quick. 60 plus or minus 4.186 gives us a confidence interval of 55.814 to 64.186. So now we want to use the same assumptions listed above, but now we're going to calculate at a 90% confidence interval for the mean age of the population which they represent. So we're going to do the same exact thing. So we know our x bar is going to be 60 plus or minus our z of 1 minus alpha over 2, because that's going to change with our 90% confidence interval. But our standard error is going to be the same because we're not changing anything there. So it's going to be 1.625. So what we have to do is figure out what our new confidence interval, z minus 1 alpha, is. This one I'm going to use just looking in the book. And when you look in the book at a 90% confidence interval of 1 minus alpha over 2, you get a value of 1.645. You multiply that times 1.625, and you're going to get a value of 2.673. So 60 plus or minus 2.673 is going to give you a new confidence interval of 57.3269, comma 62.3673. 62.6731. Moving to question 5. Suppose researchers interested in determining if there is a relationship between low birth weight and pneumonia, pediatric pneumonia, and in order to test the relationship, the researcher will use a standard deviation of 746 grams and a margin error plus or minus 646 grams. How many newborn will the researcher need to sample in order to be 95% confident? So this one we have a new formula in which we're trying to determine the sample size needed for this to be 90% confident. So our formula for sample size is n equals z of 1 minus alpha over 2 times standard deviation over the margin of error, all that squared. So one of the things I told you to commit to measure to be 95% confident of a z 1 minus alpha over 2 value is 1.96. They told us our standard deviation is 746 grams over our margin of error, which is 646 grams. When you divide and multiply out, you're going to get a value of 2.2634. You're going to square that value, and you're going to get an answer of 5.123. Or since we're dealing with people and numbers, you're not going to have 13% or 12% of a person, specifically even pediatrics, so babies. So we always round this up to the nearest whole number, which will be 6. Moving on to the big question here, which is question number 6. Suppose a researcher is interested in investigating the effectiveness of a new medication aimed to treat HIV. The following table represents the CD4 cell count for an SRS of individuals treated with the new medication. First thing in problem A, they want us to calculate a 95% confidence for the average CD4 count in the population treated with the new medication, assuming we can approximate with the normal distribution, use a population standard deviation of 24. So this one, they tell us our standard deviation is 24. We know we have patients A through R, so we have 6 here, 6 here, and 6 here, so we know our N is going to equal 18. we need to find our average, our x-bar of the sample. So if you add up all the CD4 counts and then divide by 18, you're going to get 5,499 divided by 18. So you're going to get your x-bar is going to equal 305.5. So let's write out our formula and start plugging in what we know. So in order to calculate the formula for our confidence interval, it's x bar plus or minus our z1 minus alpha over 2 times by the standard error of x. So this one, we already know our x bar because we calculated, so that's going to be 305.5 plus or minus, we know, like I said, our z1 minus alpha over 2 is going for 95% confidence interval is going to be 1.96. So we need to calculate our standard error. Standard error, once again, is the standard deviation over the square root of n, which is 24 divided by the square root of 18. So it's going to give us a value of 5.6569. Add that in our formula here. Multiply before we add or subtract. You're going to get a value of 11.0875 plus or minus 305.5, which is going to give us a confidence interval of 294.4125, comma 316.5875. Don't know why I started getting all big. And that is going to be our confidence interval for 95% confidence. So when we interpret our value above, we would say we are 95%. I'm just going to put confident that the true average CD4 count is within the interval. Part C. Assuming the researchers hypothesized that the new medicine would increase to at least 400 cells per milliliter, use your confidence interval to answer the question as to whether or not the researchers met their goal. So if we were the ones who actually did this experiment and we said that our new drug is going to increase the CD4 count to above 400, did we meet our goal? Well, our confidence interval is 294.41, we'll say, and 316.58, so 400 is outside that confidence interval. If we take a look, more closely look, none of the values of the CD4 count in any patient even reached 400. So if our goal is to reach 400, did we reach 400? The simple answer is no, we did not. Why didn't we reach it? Because our 400 value is not within the interval. So we did not reach our hypothesized goal of 400 CD4 cells. Number seven, we're going to, researchers interested in the toxicity of cigarette smoking in humans. One measures that he decides to investigate involves measuring the pH of urine from smokers to see if there's an increase in toxicity. In order to carry out the statistical test, the researcher collects an SRS of 61 current smokers from a population with a known standard deviation of 0.8. If the researcher wants to be 95% confident about his estimate, calculate the margin of error based on the information above. So now we're asked to calculate the margin of error. Our margin of error formula is m is going to equal our z of 1 minus alpha over 2 times the standard deviation over our n squared, which we can also say is our Standard error, well, we know 95% confident is going to be a 1.96 z1 minus over alpha. Standard deviation, they tell us is 0.8 divided by the square root of n, which we know is 61. When we do our standard error, you're going to get a standard error of 0.10243. You're going to multiply that times 1.96. Multiply that out, you're going to get an answer of 0.200, or you can just say 0.2, and that is the margin of error. Carry out the same calculation above, but assume the researcher wishes to be virtually certain about its estimate, so we're going to use a z-score of 3. Remember, if we go 3 standard deviations out from the mean, plus or minus, you would encompass 99.7 due to our 68, 95, 99.7 rule. So now we're going to use a z of 3. So instead of using the 1.96 we did above, we'll use the same equation. So we're going to be m equals 3 times our 0.10243 for our standard error, because it didn't change from above. And we multiply this out, you're going to get a value of 0.307. So if you wanted to be virtually certain, you would use a margin of error of 0.307. Part C, kind of carry on to the next page here. And for part C, compare from above the margin of error blank with more confidence. So the margin of error will always increase with more confidence. Alright, and that will conclude the chapter 10 problems. I will get another video up to start going over chapter 11. Have a great day.